Hey everyone, good morning. It's Faraz here, and welcome to Speakeasy JS, the meetup for mad science, hacking, and experiments. I'll be your host this morning. So glad you're joining us today. Mad science is all about building things that make people say, "I didn't know that was possible." So today we're joined by Nick. I'm going to probably get your last name wrong. Sorry, Doiron. Is that right?
Yes, that's good.
Okay, amazing. Great. Nice to have you here.
Yeah, thanks for having me, Faraz.
Yeah, of course. So yeah, I was super excited that Nick is joining us today because he is a full stack engineer and a digital nomad, and he's been living out of Airbnb since 2014. I just learned, and I think that is just wow. That is pretty cool.
Yeah, it's been great to travel all over and do. When we're in tech, we're really lucky we get to travel and work from different places. So it's been really good.
Yeah, that's super cool. I kind of think, well, we've all been, maybe some of us have been doing some more traveling than normal during the pandemic. Yeah, anyway, that's super cool. Super interesting fact about you. And yeah, so we're going to learn all about quantum computing, which I have to say I know nothing about. So I'm super excited to learn about that a bit, and then also how it combines with JavaScript.
Well, yeah, that's a great place to get started with. Like, even if you don't know a lot about quantum computing, I'm not a quantum physicist. I did not do like a computer science degree in this or anything like that, but just coming into this as a web developer and saying, what can I understand about this and what can I do in this very rapidly evolving and changing space of quantum computing?
Mm-hmm. Well, great. I can't wait to hear it. So yeah, feel free to get started.
Yeah, cool. So titled Ready or Not, Quantum Computers in JS. A little bit about me and my day job, not to ruin the mood with US politics, but I work in a redistricting and anti-gerrymandering program. For people not outside the US, we just completed the US Census last year. So all of the congressional and city council districts are redrawn to balance the amount of people in each district. I also have some side projects in natural language processing, and my kind of top Hacker News link that I've ever had is Fortran.io. But we're going to talk about quantum computers today. And my connection to quantum computers definitely was entirely a side project, yet it's one of my side projects that has the most legs in terms of it's the one thing I'm mentioned for in a citation on Wikipedia, and it got me into a conference at the International Atomic Energy Agency in Vienna. So that it's such a bizarre space, and there's a lot of different people working on this problem that it's great to interact with them during this. So quantum computing has been getting a lot of interest, a lot of hype recently. These are some headlines that I've grabbed over some time. Google getting quantum supremacy, so-called quantum supremacy, and Amazon also launching a quantum computing service. China, Europe, and the US each investing over $1 billion in research into quantum specifically. So what makes people really excited about quantum computing? So if you're familiar with Moore's law, the idea is that over time, our computers are getting smaller and better and cheaper all at the same time. That's how computing is moving so rapidly. So, the first generation was, the like weaving looms and then vacuum tubes and then transistors, which we now use in all these different chips. But now people who are researching in transistors have made transistors that are the size of just a few atoms. And that's the theoretically physically smallest that you can make a transistor. So we're hitting kind of a wall there where people are wondering, what happens next? How can Moore's law be continued? And there are a lot of different theories out there with photons, lasers, doing different three-dimensional things. But as you will recall, the topic of this talk is quantum computing. So I'm just going to focus on this idea, which is that quantum computing could, for particular applications, be much more powerful and faster than classical computing with transistors, and be an entirely new generation of computer compared to that same change from vacuum tube to transistor. And the applications it's useful for, you probably wouldn't need to run a web browser in a quantum computer, but it can be useful for particular tasks, which even at a small scale would have a great commercial application. So these are the top three areas where I see the most interest in quantum computing. One being simulating quantum chemistry. If you think about it, rather than simulating these molecules and forces and things like that inside of a classical computer and dealing with all those possible options and interactions, it might be more helpful to have a computer have quantum molecules inside of it where those are interacting in a particular way and doing computations in a particular way that is more native to that actual problem space. The second one that I see, whenever you see a few different words together, like quantum, blockchain, ML together, you think this is just all hype. I don't want to listen to it. But there is an actual interest in eventually doing some type of machine learning in quantum computing because it can be applied over a very large function. And so potentially be easier. It'll be easier for it to find the absolute minima or absolute maxima, depending on how you're creating your function. And that would make it easier to use these quantum devices to train on this machine learning problem. I think the most famous one, though, which I don't know if people have heard about this before in association with quantum computing, but it seems to be the most famous one, is that quantum computers can be used to find the prime factors of a number much faster than classical computers. Where in classical computers, it's seen as a exponentially difficult problem. In the quantum computer, it is a linearly difficult problem. So problems which encryption, which you can safely say will not be cracked with a classical computer, will actually be somewhat easier to do in a quantum computer once we have a quantum computer that's the right size. We don't know when that's going to be, probably in the distant future, but it's something that we have to talk about because it would be a huge deal. If I don't know how familiar people are in the audience with different kinds of encryption algorithms, but AES, ECC, RSA, these are all based on factoring prime numbers. Like each side has the knowledge of the prime numbers, so they're able to communicate to each other, but someone who's intercepting is not able to factor it out. Well, in this case, if you have the quantum computer, or if you're collecting data now, this is something people are also concerned about. If you know you're going to have a quantum computer in the future, you might be collecting data now to decrypt later on the quantum computer. So there's a real fear that problems that we've relied on being complicated will become easier once a large enough quantum computer is built. And I should clarify, this is not the same thing as P equals NP. Those problems are not useful for encryption because they're very difficult for both sides to compute. And the quantum computer does not make that any better. This is just specific problems that people have already studied and come up with quantum circuits that can help them solve it. So people have known about this for a long time. Shor's algorithm, which is what this is based on mostly, was published in 1994. And the Tom Clancy novel Night Moves in 1999 had a quantum computer as one of the key plot points or something like that. It's been a while since I looked at it. So people have known about this for a while and said, you know what, there are no quantum computers here. We don't have to think about it. But the time is getting closer. Now there are actual multiple startups, major companies like Microsoft and Google with research teams. We'll talk about how many qubits they have now because that's a little bit controversial. But now that people are saying, okay, we have run a quantum computing problem, maybe we should take this a little bit more seriously. So some examples of how people are responding to this is in Google Chrome, they have just randomly selected some users to encrypt their data with both the current AES encryption and a new kind of encryption called lattice-based encryption, which is believed to be post-quantum effective. Microsoft has been advising companies that have their profits far off into the future. For example, pharmaceutical corporations. There's so many, let's say like even 10, 20 years of development into a drug that you don't want those emails to be decrypted, to be collected now and then decrypted and used for some kind of espionage in the distant future. So Microsoft started advising particular industries that they should look into this post-quantum encryption already. And the National Standards Organization for the US, NIST, is running a competition right now where there's different competing standards for post-quantum encryption that they're evaluating and letting other people look at. And this is a very tricky space because, one, we don't have a lot of quantum computers to test against. We don't have a lot of quantum computing experts to look over the algorithms and, challenge these different proposals. And also, you can't just develop something that's useful against quantum computers. It has to be useful against quantum and classical computers because you don't want to start encrypting everyone's data for these theoretical quantum stuff in the future and in the process expose people's data because you used a brand new algorithm that hasn't been fully vetted. So they're trying to find the right way to experiment with it and not have like a performance loss or build systems that will become outdated and vulnerable in the future. So the problem one, which I think we talked about a little bit in the beginning, is Richard Feynman, famous physicist, said, I think I can safely say nobody understands quantum mechanics, which is to say that there isn't, like a little toy kit. Like you can get a kit that gives you like little circuits and kind of learn a little bit about, electricity goes in a circuit and play around with it. There isn't like a physical analog that you can play around with your hands that covers the intricacies of quantum mechanics, quantum chemistry, things like this. I don't really expect as a programmer that I'm going to understand it in the same way that, if I were on a desert island with a chip fab, I wouldn't be able to say, okay, I'm going to learn how to put together transistors and learn how to put together chips and learn how to put together a CPU and learn how to make it start running JavaScript, because there's so many steps in between that physical level and the application. If I'm just a developer on the endpoint, maybe I just need to know what are the useful applications and what is really going on in there, like how people are programming it today. So the one thing I would say that would be a good thing to look into if you're trying to understand this space is there's something called the block sphere, which is how people represent each qubit. So in classical computing, you have bits that add up to a byte and so on. In the quantum computing, you have qubits. And sort of the popular news story thing to say is that they're both 0 and 1, or they could be both 0 and 1. That makes you wonder, like, what's the usefulness of something that you don't know if it's 0 or 1? What's the usefulness of that? So what was really helpful to me to read more about this is that they're not really 0 or 1 randomly. There is a probability space that these are in. So you could draw it as a function. You can draw it as this kind of sphere. And that's the probability that so it's in this quantum state right now. And if something that is not in superposition, okay, so it's in superposition right now. If something that's not in superposition hits it, then it will resolve into a 0 or a 1. So typically that's done with shooting them with a laser, pretty cool. And then it'll resolve to 0 or 1. And then if you run multiple experiments, you'll say, okay, 10% of the time it was 0, 90% of the time it was 1, and you can use that to represent what was its probability state at that point of the program. So not fully easy to understand, but this was the part where I understood, okay, it's not just like a random number that we're trying to get value out of. In fact, there's one thing I read that compared it to more like analog, like pre-digital computing, because it has a value that is neither 0 nor 1, but more of like a probability function or wave. And that wave can be shifted, that wave can be modified. And then when you have multiple qubits that are in superposition, you can entangle them in some way, so that if this could be a few different options, and this can be a few different options, you can cross them or entangle them, and now you have multiple interactions happening in that probability space. And then you run the program multiple times, you shoot the laser to measure it, and then you come up with a representation of what was the final probability. Problem 2, the hardware to run this. If you imagine that if anything hits something that's in superposition, it's going to drop out of superposition. You can't have this be in open air. So something like this that you might see a picture in the news, they put it inside of a vacuum, they cool it down to absolute zero so that the molecules aren't moving around like that. They sometimes use lasers to shoot them into not moving around so much, something called laser cooling. So long story short, you're not going to have a quantum computer on your desk. Like if you have a lab where you might have a absolute zero freezer, maybe it's possible, but these are always going to be, or for the foreseeable future, they're going to be extremely complex devices that are used kind of as in a cloud computing center, and you interact with them over the web. Okay. So how many qubits? Right now, if you look at Wikipedia, they're saying the top one is 76 quantum computing or superconducting qubits. So when that number gets up into the thousands, and they're all entangled with each other, then there'd be an encryption issue. So that's why it still feels very far away. And you can also see these are from 2018, 2020. These numbers are not going up exponentially right now. It's very difficult to figure out how to build these, how to make them work reliably. And then also you actually have to physically design the chip so that they can connect with each other. So there's like a topology of building the gates in between each qubit in the chip. I'll also say that there's a company called D-Wave, which will say that they have hundreds of qubits, and they do, but those are a different kind of qubit through quantum annealing. So you can't compare different hardwares to each other based on that number. So they're useful for other applications, but it's not the same number that they're comparing apples to oranges in that case. So like I talked about earlier, you program bits by connecting these bits together with gates and coming up with some kind of processing out of that. And then eventually you have assembly, compilers, and then JavaScript. In the quantum world, you have the qubits. They're connected by these quantum gates. Right now, a lot of development, like I said, is going into the hardware and topology of the chip. Then even if you have multiple qubits, those are like the physical qubits in the sense. There's a problem, which is there's a lot of noise and there could be errors. In digital computing, we know how to do error correction in like connections. In quantum computing, you can't do error correction against something that's against a classical bit, because to measure a value, you have to take it out of superposition. So in order to make a qubit that can correct for errors, you need to have multiple physical qubits in connection with each other. So this is like a theoretical thing that hasn't actually been built and tested yet, but it could mean that even if we have 100 physical qubits, you might have 10 logical qubits or error-corrected qubits. So there are a lot of algorithms being developed, but the number of qubits we have is very small and noisy. So these algorithms are not like ready to run. So how long is it until we can run something like Node? Just probably not. It's just so different. The way that people are writing programs for quantum computers right now, mostly in Python. These are two different libraries. You say that you're going to build a circuit that has, like, in this case, 2 qubits, and then you specify the particular gates. Like this is like down to the assembly and gate level design of your program. And then you run the measurement. And then, like I said before, if you look at the bottom, it says trials equals 10. I'm saying do this program 10 times and tell me what were the distribution of results. The first attempt that I did to work in this space was so Rigetti Computing, which is a startup that has a Python library. I sort of cribbed off of their Python library to make a JavaScript library called JS Quill. So they have PyQuill and mine is JS Quill. And like you can see, it's a pretty similar idea of I'm going to make a quantum program. I'm going to add these particular gates to these particular qubits, and then measure and run based on that. So that came out, I want to say 2017. Yeah. So I was able to put that in 2017. This is linked the link that I have on Wikipedia from somebody. And it was really interesting. I still get interest in that to this day, but I wanted to rewrite it because there's many other quantum computing providers right now from Microsoft and Google that are running their own cloud quantum computer, even with these small number of qubits. They don't always call their gates the same thing. And there also have been some changes to the API. I also have a bad habit of like just kind of hacking something together and not testing how everything worked out. So I wanted to rewrite it in TypeScript, which was really big whenever I was thinking about this a couple years ago. And just to give you an idea of how similar these things are, these are 3 different libraries, but you can see they're all, the little box I wrote, they're all doing the same thing. They're doing an H gate, a CX or C naught gate, and then they're measuring something. So why are there these 3 different Python libraries that are written differently? And really, I could probably write something that in JavaScript that would compile down into each one of these, because they're all doing very similar things. So the library I ended up creating, it's called Quantum Peep. My pitch for it was write once, run anywhere. So that same program you were looking at earlier in Python, there's an X gate, a C naught gate, and then you do the measurement. And then on the right column, you'll see that I can compile it to Quill, which is the Rigetti program, Q#, which is the Microsoft assembly type language, and Chasm, which I believe is the IBM type assembly. So these look very different, but you can build your program in the same way. So you can do this kind of compatibility of whatever you're familiar with writing, and then run it on another platform. The road ahead, this is my last slide. Adoption is very slow. IBM even had their own JavaScript library called Qiskit.js, and now they've just completely gone over to Python, since that's what most scientists are using. I still see a lot of people interacting with JS Quill. I archived it and told people that Quantum Peep is newer and more compatible, but people don't really seem to see that. They just want to find some JavaScript quantum thing. We don't have like a hello world program where people can run it. Like, with Arduino, you run a program and the light blinks and you think, okay, I know how to code. With this, we don't really have like a getting started with quantum computing. Like this is basically the hello world is like create a gate and then do a C naught, a controlled NOT gate like this. People don't really feel inspired by it. They're like, what am I doing? What's going on here? So it'd be great if we got enough qubits that people could do like a really interesting quantum random number generator type experiment that was interesting to them as like a hello world problem. Also talking about the dangers of post-quantum encryption, or dangers of quantum computers and need for post-quantum encryption at the International Atomic Energy Agency was one of the greatest experiences of my life. If you think there was like a 1% chance they contributed 1% to preventing a small nuclear exchange, I think it was the most impactful day of my life, if you think about it that way. But yeah, if you just a little pitch, if you can get involved in any kind of program that helps control nuclear, chemical, biological, or AI weapons in our field, even if there's a small chance that you can help a little bit, it can have a huge impact on our livability of our future. Not to like put us into a weird mind space, but it was really interesting meeting those people and finding out what they're working on. So I wanted to make a little pitch for them. So yeah, this is the node module. This is my GitHub and Twitter as MapMeld. And we went through this very quickly, so I'd be happy to talk in more detail about some of these quantum programs and how you just kind of wrap your head around it.
Thank you so much, Nick. That was amazing.
Okay.
Thank you. Appreciate it. So if you have questions now, you can ask them in the chat and I'll relay them to Nick. And we'll have a little bit of time for questions before we go to our social happy hour on the Rambly platform. But yeah, I think I guess my first question is, have you used Quantum Peep for anything interesting yourself? Like what are the most interesting programs or things you've done with it?
I was really happy when they had Rigetti had and IBM both had a thing where you could run against an actual quantum computer, because they will host a simulator and then occasionally they'll allow people to run a program against an actual quantum computer, and it gets into a queue and then it runs it and then it emails results back to you. That was really exciting that I was able to write something in JavaScript at home and then like run it and then get back something that someone actually built a quantum computer somewhere. Because definitely like 5 years ago, the thought was, do quantum computers even really exist? Maybe there are a few qubits people have built and tested. So to have it be so readily available on the internet, and that was really, I feel like it made it seem so much more real at that point. But no, nothing. I'm not like I've interviewed at a few places that are doing these more professionally, but I haven't had this kind of a problem where I thought, oh, I need to use a quantum computer for this.
Mm-hmm, mm-hmm. Yeah, that it does seem like that is the stage that things are at. But I totally get the excitement about knowing that you wrote code in JavaScript that eventually later ran on a real quantum computer. That's super cool. Yeah. So have you got a sense for what people are using the library for? Do you know who, like, has anyone kind of anyone interesting kind of like made issues on the GitHub issue tracker, or like, are there any secret agencies using it for something?
I always get a little nervous when I get a GitHub star from someone in a country where the US is not supposed to be doing technical business with. So that's always a little exciting, but I really encourage everyone to do it, because right now it's just it's a physics problem. It's not like, I don't really believe it's something that needs to be kept secret. What I would say about it is I think most scientists are just using the Python thing, because that's a very sciencey kind of thing to do. It's very, like, a lot of researchers are doing that. So I think really what is happening with this and why there's no compatibility between these different Python libraries either is there's this thought that if we convince researchers to use our toolkit now, there'll be this buy-in, and in the future, when they do larger scale commercial quantum experiments, they're going to be more partial to this company and their platform. So it's really like another cloud computing war over which cloud computing provider is the best, but then they also control how you program the computer. So I hope that there can be more of a generic thing. And Amazon Bracket, I mean, they have their own quantum computer team, so I'm not sure what's going on with that. But they do have some kind of similar cross-platform abilities for a few different providers.
Mm-hmm. This seems a little bit similar to NVIDIA's CUDA framework that's proprietary, and how, like, they kind of, for a while, I remember, like, there were even classes at Stanford when I was there that were specifically like teaching you CUDA, this proprietary framework. And then later on, when AMD wanted to like get into the space, they I think they were the ones who created OpenCL, which is like the open source version of CUDA. And they have, it's funny, like the company that's behind Howells has an incentive to create like an open source framework or standard for things, because it just benefits them to convince people that this proprietary thing is bad and they should use the open thing. And then anyway, so I don't know what the state of like that kind of computing is. I think OpenCL is pretty popular, but I don't know how like whether it's overtaking CUDA or what. It sounds like it's just a similar thing playing out again in quantum, and these companies are hoping that you're gonna like choose their library and get sort of locked into it.
Yeah.
So were there any things you couldn't do like easily across were there any sort of, I guess, things that were so different, like operations or instructions that were so different that you couldn't make something unified?
Yeah, the one thing that I had a heck of a time trying to figure out was there's particular gates that you give it, and a number the parameter that you give it is the gate and a particular number of degrees or radians. And then I found out in one case, if you send it, let's say you send it 0.25, then that means like pi fourths radians, right? Which is a normal number in math. But then I'm trying to think, okay, if someone writes 1/4 in my code, should I multiply that by pi? Should I turn it into radians and degrees, or how should I represent it? And then how do I write it into the code? And they don't have it was really tricky finding examples in their own documentation to know whether it was expecting it to be a number or the number to multiply pi by, or just even finding something like that. The documentation is not very easy, and then they assume that you are a quantum physicist, so it's like a what kind of gate? I have to look up. Are these names meaning the same thing? Things like that.
Mm-hmm. Yeah. I'm curious, like, I think maybe you explained a little bit at the beginning, but maybe you could talk more about, like, how did you get into this project? Like, and how do you maybe more generally choose which projects to work on? Because it sounds like you mainly maybe didn't have a specific use case in mind when building this. So I'm just curious to know more about why you've gone so deep into this area.
Yeah, so not to make a whole thing about blockchain or anything, but 2011, I'm in Uruguay working on one laptop per child, and I read an article about Bitcoin. And I thought, oh, interesting. And I talked to somebody about it, and it was ever, and now that person I talked to about it, they invested maybe like $30 into Bitcoin, and now they have tens, hundreds of thousands of dollars, right, based on that. Whereas I was just like, oh, that's really interesting. I was like thinking about it just very theoretically of like, I need to have this in my mental model of how the universe works or what people are doing. But I never thought I literally should spend a day on this and find out what people are talking about. And as a result, I didn't really think about that until, years later when I'm saying, okay, now I really should pay attention to this. So now for me, when I'm hearing about, in this case, quantum computing, I was also interested in Fortran for a little bit. I was like, that's something I've heard of. I know that some people are still using it, that there's like some kind of problem in finding people who understand this. So maybe I should understand this in case it becomes more useful. And no kidding, one of the things I got on LinkedIn when I interviewed with a quantum computing company, they contacted me on LinkedIn and said, JavaScript and Fortran, we use both of those at our quantum computing lab. And I was like, really? Like, how could it possibly be? But, they're doing that like low level, very fast monitoring of their hardware. So they needed something that was like C or Fortran or something. So it's interesting to think about finding these particular niches. I never finished my undergraduate degree. So for me, it's always been finding a job through, they're like, oh, how could we ever find somebody to do this particular thing with mapping or quantum computing or something? And then that really goes a long way to getting in the door of saying like, oh yeah, I know a little bit about this. I haven't done it in production, but so on such and such. Yeah.
Mm-hmm. So is there a public simulator or something like that to try out? As someone's asking in the chat about, like, is there a way that they can try it?
Yeah, I saw that question. So IBM, I think, still is running like a web UI where you can put together a program in the IBM language and then run it and get some info back. And it has it's a little UI there. Amazon Bracket, you have to, there's a write-up on AWS Docs, which explains you have to invite their quantum user as a permission on your notebooks or something, but then you can write something in the SageMaker notebooks on Amazon. As for my own thing, I used to have just a quantum simulator running in the cloud, and then when you use the app, or not use the app, when you use the library, you could send your program to that. But I don't believe that anyone was really using it. It sort of felt like, why am I, running this? I really think that the company that open sourced that simulator used to have one running all the time, and I really think they should keep that going, because it was always like that greatly reduces the barrier to entry, is if someone is running a simulator somewhere, even with a few simulated qubits. So you can just say, okay, I'll send you this, and then does that run? Does this work? How do I structure my request or my program to be like the library? Because that part of it isn't documented very well.
Mm-hmm. So you can simulate a small number of qubits, it sounds like, but
Yeah.
like, at what point is it impossible to simulate? Like, is it are the actual quantum computers that have these small numbers of qubits, are those simulatable, or does it quickly get out of hand?
Yeah, so the number I had heard before was something on the order of like 50 or 60 qubits that are entangled with each other. You would then need the most powerful classical supercomputers when you get up to that point. So we now have quantum computers that do that. At the end of 2019, Google did what's considered to be the first quantum supremacy experiment, where they were able to do something in quantum computing which would have taken multiple weeks to simulate on a very large supercomputer. The thing that's a little bit sketchy about it is they invented a problem. It wasn't a practical problem where they were like trying to do some material science or something. They said, oh, if we had this particular question of this distribution of numbers, like they designed an experiment specifically so that it would be easier for a quantum computer to do it. And then IBM's team, because they didn't want to be seen as being second at quantum supremacy, IBM's team said, actually, you could do that experiment with like doing this with your classical file system on a supercomputer. So they had a really interesting dialogue about what is possible to do for this problem, and whether it makes sense to talk about this problem when it's not really a problem that real people have. It's more like designed to be, who can compute this better. So then since then there have been other problems like this that people have created and done a quantum supremacy experiment. And I think there's just like 2 or 3 examples that are published that people have done this. But it's really interesting to think about that eventually, I guess that's the first step towards finding a problem which is useful and would be cool to get the quantum computer doing it faster than a classical one.
Mm-hmm. Yeah. Cool. Well, I think that's all the time we have questions for now. Is there anything else you want to tell everybody before we go?
No, nothing in particular. I did see a couple questions asking, is this the end of encryption and privacy and secrecy? I mean, I'm hopeful that the post-quantum encryption methods that people have proposed can be evaluated by NIST and various researchers, and then people can come to some conclusions about how useful they are. And I think it's just more of like an accident of how we designed to decrypt encryption in the first place. We never figured that there would be this kind of other hardware that would come out and make it obsolete in the future. So it's more like we need to have this transition over. But if you think about like something like IPv4 to IPv6, even if people know it's coming for years and years and years, you're still going to have people not knowing what's going on or how to implement it. And it's definitely something that is going to be over multiple years, people figuring out, is our system compatible? Are we ready? Is this causing some kind of additional problem? But I'm optimistic about it for sure.
Mm-hmm. Cool. Well, thanks so much for making this understandable for us today, and for making this library and just explaining like laying everything out in a way that's surprisingly understandable. So I appreciate that.
Yeah, thanks for hosting.
Yeah, of course.